What might this mean for humans? How might this be applied to humans? Do humans have this programmable layer just as some of these other species do? What might therapeutics or morphoceuticals or otherwise look like?
So a couple of things to explain why this is relevant to humans, and then I'll give you like three broad areas of application. The reason it's absolutely relevant to humans is that we are all basically built on fundamentally the same principles. People have this idea that, well, frogs are sort of a lower creature, but we're mammals, and once you get past yeast and things like that, we are all roughly the same. As far as this stuff goes, these kind of electrical signals evolution discovered them around the time of bacterial biofilms, like very long ago. And so this is all very well conserved. And for that reason, for example, there are human mutations in ion channels that are birth defects. So if you mutate ion channels in humans, you get birth defects just like we see in frog and chick and zebrafish and things like that. So those are all well conserved. And with David Kaplan, who's a collaborator of mine at Tufts, we've done a bunch of work on bioelectrics of human mesenchymal stem cells. This stuff works for humans as well. It is not some like frog or flatworm specific thing. This is very, very broad. I should say, this is a disclaimer I always have to do. You mentioned morphoceuticals. So there are a couple of spin-off companies that have licensed some of this technology. So I need to sort of say that as a disclosure. So one is specifically called Morphoceuticals. There's a company that is pushing forward our limb regeneration work in bioelectrics. And then there's also this other company called Astonishing Labs that is doing some of the stuff in aging and so on. Having said all that, I firmly believe that these things are heading for clinical application in humans and probably not that far off, I hope. Here are the three applications. So the first application is birth defects. So we have shown that we can repair a number of different birth defects of the brain, the face, the heart, what else, the gut, these kinds of things by restoring correct bioelectrical patterns in vivo. And so this is now in animal models. We are moving, of course, to more clinical kinds of things. And I hope in the future, this will absolutely be of human application. So birth defects is one. Regeneration is another. The name of the game here is communicating with the cells. This is not about stem cells or gene therapy or scaffolds made of nanomaterials. Like those are all tools that might be useful. But the real trick here is to communicate to a group of cells, what do you want them to build? And that's what the bioelectric code is all about. It's about communicating to the collective, to the cellular collective. And so we've done work on limb regeneration. We've done work on inducing whole organ formation, eyes, and things like this. So I think there are going to be massive applications, hopefully clinically, in restoring the damaged and missing limbs and other structures like that. And then the third thing is going to be cancer. So something else, and we can get into what the kind of more profound aspect is, but the bottom line is that cancer fundamentally involves an electrical dysregulation among cells. I'll just say it and we can unpack it later, but it's basically a dissociative identity disorder on the part of the cells. It's literally a disorder of the cognitive glue that binds individual cells towards large-scale purpose, where large-scale purpose, I mean building organs and tissues and things like that, as opposed to being amoebas and doing amoeba-level things. So cancer is another thing, and we've shown, again, in these animal models, both that we can detect incipient tumor formation, and we can prevent and normalize tumors after they form by restoring, not by fixing the DNA if there is any DNA issue, which there doesn't have to be, not by killing the cells with chemotherapy, but by electrically reconnecting them to the group such that they can form, again, a memory of what they're supposed to be doing. So those three things, regeneration, birth defects, and cancer, I think are going to be of great value in humans. Now, there's also issues of aging. So we also have an aging program in our lab and looking at why it is that over time cells forget how to upkeep a proper organism. And we have some interesting thoughts about that as well.